We have repeated eigenvalues. And I'll say parenthetically real or complex. And this case actually subdivides into two other cases. So we're going to have a case 3A and a case 3B. Case 3A. If there is no defect, well, it does seem reasonable at least to consider this because, as you well know, when we have repeated eigenvalues, another way to say that is that you have an eigenvalue of some multiplicity greater than 1. And as you know then, we can have anywhere from one associated eigenvector to the multiplicity. We might have that many linearly independent eigenvectors, but a lot of different things can happen. So if there's no defect, it's really very different from if there is a defect. So if there is no defect, actually the situation is very simple. Then the solutions have the same form as for distinct eigenvalues. So nothing new to learn, no tricks, no adjustments. It just is what it has been. So let's do one quick example. And as I've been doing all the way through this section, I'm being lazy and picking on examples that we've seen before so that I don't have to run through and find the eigenvalues and eigenvectors. I already know them. So this one was example 2 from section 8.8. And if we go back to example 2 from section 8.8, we will remember that these are the eigenvalues and eigenvectors. There was an eigenvalue 0, which corresponded to the eigenvector negative 3, 2, 1. And then the second eigenvalue was 1. I hope you don't mind if I'm abbreviating multiplicity 2. I'm just saying mult 2. And it came with 2 linearly independent associated eigenvectors. And again, you don't know ahead of time that you'll get 2. You might sometimes just get 1, but in this case there was no defect. We did get a pair. And in that case, our general solution is obtained just as it would be if we had distinct eigenvalues. So, if you remember the pattern, it's simply eigenvector times e to the eigenvalue times t. So in this case, C1 times the eigenvector negative 3, 2, 1 times what? Times just 1, e to the 0t, so we don't even have to show that, plus C2 times the next eigenvector, negative 1, 1, 0, e to the, this time it's 1 times t, plus C3 times 0, 0, 1, e to the t. And we are done. And you may feel a little bit uncomfortable with that. You may feel like, now wait a minute, when we have repeated roots of a characteristic equation, I would get something like e to the t, and then a different solution would be what? If I had a 1 and a 1 as roots of a characteristic equation. T e to the t. A lot of you remember that. It's not the same here. Here, in both cases, we just have e to the t, but you can still see that we still have linear independence because those e to the t's are multiplied by different eigenvectors. So they still are linearly independent. If you tried t e to the t, in fact, it wouldn't work. So this is the way that the solutions are built. same way as if you had distinct eigenvalues. So that's case 3A. That's a nice one. Now for case 3B. What if there is a defect? If there is a defect, in other words, if we cannot get as many linearly independent eigenvectors as we would like, then it is possible, but more difficult, to find linearly independent solutions. Now, the fact that it's possible, I hope, doesn't surprise you because of our theory that we talked about on Tuesday. The set of solutions is still a vector space of dimension, in this case, whatever it would be, matching the dimension of your system to start with. You still hit a vector space of that full dimension, so it has to be possible, but it is very much more difficult. You have to do find something called generalized eigenvectors, and it just takes a lot more work. It's doable. And you may or may not like this next statement. We will not go into the details. Basically because we have other things to do this semester, and this is not one of the most important considerations. But I do want to assure you that it's possible. If you really care, you can look it up, or you can come talk to me. I can show you my notes on the subject, but we're not going to go there. So basically, we are done with solving systems of linear differential equations using eigenvalues and eigenvectors. So I promised you on Tuesday we were going to do some picture drawing. So we get into the last topic here, something called phase portraits. And some of you have done these before. Basically drawing pictures of the solutions to a system of differential equations. But we're going to go for the simplest kind, just a 2x2 system, all constant coefficients, everything linear, as nice as can be. So consider a system of DEs, differential equations, of the form. And here's the form that we're going to be looking at. Pretty much the simplest form you can get for a system of DEs. X prime equals AX plus BY. Y prime equals CX plus DY. So two equations, two unknown functions. Remember, those are all functions of t, the x and the y. Linear, homogeneous, constant coefficients. Pretty much the simplest thing that you can get. Let's talk about what it means to find solutions. The solutions are, well, again, remember that these are all functions of t. And what you're saying is that how x changes over time, this x prime is a dx dt, not a dx dy or something like that. How x changes over time depends not only on x, but also on y. How y changes over time depends on x and y. The solutions then are going to be the function x and the function y, both given in terms of t. So the idea is as time passes, x changes and y changes, and therefore you have ordered pairs that move around. So you get things that are moving around, ordered pairs, points in the plane that are moving around as time goes by. So these solutions, whoops, I'm messing you up here. I didn't want the word R yet. I hope you're using pencil. The solutions, which happen to be of the form vectors of functions, x of t, y of t, are parametric equations of curves. So in other words, you get curves in the plane, but they're moving around. They are traced out as time goes by. They depend on the parameter t. So what is a phase portrait? Well, it's a fancy way to say we're going to draw something. A phase portrait is a picture of some of these solution curves or trajectories in the xy plane. Or sometimes it's called the phase plane. Just another way to say the same thing, just the xy plane, the coordinate plane. We often use the word trajectory because that gives a little bit more of a sense of movement. It's not just a static picture, it's a curve. We're thinking of that curve being traced out as time goes by. Note, let's look at this particular solution. X of t equals 0, y of t equals 0. I kind of already gave it away when I used the word solution. But let's double check it and see. If we're talking about x being 0 constantly over time and y being 0 constantly over time, does that satisfy both of these differential equations? It certainly does. If x and y are both 0, so are x prime and y prime, everything zeroes out and it works. So basically this is the most boring of solutions. You just sit there on the origin as time goes by. Life is going on all around you, other things are happening, but you just stay put on the origin as time passes. So this is a solution and is constant over time. We thus call the origin an equilibrium point. It kind of gives you the sense of balance, of steadiness, of stableness. Nothing interesting is happening, you're just standing there, but it is stable, it is balanced. We call it an equilibrium point. All right, well, we're going to learn by doing. So we're just going to take a look at a number of examples of these systems of differential equations and their solutions, and we're going to draw pictures. So here is one that we have looked at before. X prime equals 5x minus 8y, y prime equals 3x minus 9y. And you may want to write yourself a note that this was solved previously. We did this on Tuesday. So here is the solution. I could say general solution. X equals C1 for 1 e to the 3t plus C2 2 3 e to the negative 7t. And you might remember where that solution came from. Recognize these as eigenvectors of the coefficient matrix, and the 3 and the negative 7 were eigenvalues of the coefficient matrix. That's how we came up with that solution. I actually prefer to write it this way, just reminding myself that capital X is a vector, little x, little y. So it also can be useful sometimes to remind myself that the e really gets multiplied in. So this is 4e to the 3t, e to the 3t, plus c2 times this solution, 2e to the negative 7t, 3e to the negative 7t. I think that's a little better form because it helps me see what x is all the way across and helps me see what y is all the way across. So we want to come up with some solution curves, some trajectories, graph them and see what the picture is. We take it in stages. So let's try to begin first of all with some of the simpler trajectories. So what I'm going to first do is to take C2 to be 0. So in other words, I'm going to wipe out that second term and see what kind of picture I get by just looking at the first term. Because we want to graph lots of these for all different values of C1 and C2, so we may as well start with the easy stuff. that means that x equals, if we follow along the top line, 4c1 e to the 3t, and y equals, following along the bottom line, c1 e to the 3t. So as time goes by, this is what x equals, and this is what y equals. But then what we're really interested in is what x and y are in relation to one another. In other words, what actual points are we getting? So if x equals that and y equals this, then what is y in terms of x?
One-fourth x.
1/4 x. Now some of you look at that and you say, well, I know there's a relationship with a 4 in there, but I never know if it's a 1/4 or a 4. It's easy to get it backwards. Some of you have no trouble with that, but some of you do. My recommendation is if you're one of the people that have trouble seeing if it's y equal 1/4 x or y equal 4x, actually substitute. So for example, you could actually substitute here, the c1 e to the 3t is equal to y. So in place of the c1 e to the 3t here, put the y. So then you see that x equals 4y, and then you can solve for y. But actually do a very specific substitution if you're at all unsure. But you're right, y equals 1/4 x, and this has a name, this particular line. The line y equals 1/4 x is called, well, let's see. It actually comes out of that eigenvector, and since it's a line that comes out of an eigenvector, we are going to call it an eigenline. So we call it an eigenline since it goes in the direction of the eigenvector, for 1. So eigen everything else we've got so far, now we also have eigenlines. All right, now let's figure out how to graph this, because you do not just graph the whole line. Don't assume that just because we've come up with y equal 1/4 x that you get the whole line. You actually get pieces of it. So let's do some analysis a little bit further. So thus far, we're still under the case c2 equals 0. That's not there. So now let's think about c1 being positive or negative. Obviously, if c1 equals 0, we're back to the equilibrium point. We're back to the origin. But if c1 is positive, then the trajectory what? Well, let's see. First of all, well, let me go back to right here. If c1 is positive, then both x and y are positive, so we're in what quadrant? The first quadrant. And as time goes by, are x and y moving towards 0 or away from 0? As time goes by, as t increases, what's happening to both the x and the y? They're moving away. They're getting bigger and bigger and bigger. They're moving away from the origin. So if c is positive, c1, then the trajectory follows this eigenline y equals 1/4 x in the first quadrant. Moving away from the origin. So that's what's going to happen, and we'll start the picture in a moment. But let's look at the other case. If c1 is less than 0, it, meaning the trajectory that we get, follows y equals 1/4 x, where? This time, if c1 is negative, x and y are both negative, so this time we're in which quadrant? the third. And this time, are we moving away from the origin or toward the origin as time passes? Still moving away. We're still getting bigger and bigger numbers, except this time they're bigger and bigger negative numbers. So it follows y equals 1/4 x in the third quadrant. Moving away from the origin. So now we're going to begin our big picture. So far we're still just looking at the subcase where C2 equals 0. If you're toward the bottom of the page, you may want to begin at the next page so that you can draw yourself a nice big picture. All right, so I'm interested in the line y equals 1/4 x. But I do not graph the whole line. Remember, the equilibrium point is a solution unto itself. There are no solutions then that pass through that move in and move back out from the origin. The solutions are on either side of it. So we have one trajectory or solution curve that follows the line y equals 1/4 x in the first quadrant, moving away from the origin. So it's going to look something like that. Kind of missed. Hopefully your picture is better. And then we have another solution that is along the same line that's going to be moving away from the origin in the third quadrant. Neither trajectory goes through the origin. Those are two separate things. Actually, three separate things if we include the origin itself. So any questions on that first situation where we've taken C2 to be 0? Okay, we can go through the next one a little more quickly now that you kind of see how the game is played so far. So next take C1 equals 0. So then what do we get? If C1 is 0, that means the first term wipes out and everything is all about the second term. So that's 2C2 e to the negative 7t, and y equals 3c2 e to the negative 7t. These trajectories lie along the eigenline. Well, what's the eigenline in this case? Y equals what? What will y equal in terms of x? Hint, it's either 2/3 x or 3/2 x. Which one is it? 3/2 x. Y equals 3/2 x. And again, if you're at all unsure, this time it's not quite as easy, but say, for example, you solve this one for C2 e to the 7t, that would be y over 3. Plug y over 3 there. Do something where you're actually doing a substitution very carefully mathematically, and you'll get it. So these trajectories lie along the eigenline y equals 3/2 x. Now, which way are they going? As time passes here, are the x and the y moving in toward the origin or out toward infinity? In other words, as t gets bigger and bigger, what's happening to the x and the y? They're getting smaller and smaller because of the negative up here. So these trajectories lie along that eigenline approaching the origin. All right, y equals 3/2 x. Let's put those in. So they'll be going through, let's see, that point and that point. But this time, that was terrible. Let me try again. Okay, this time we put the arrows on this end. I truly hope hope you are a better artist than I am. Because this time the trajectories along the eigenlines are approaching the origin. Again, they do not go through the origin. Any questions on that part? Okay, now for the hardest part then. If neither one is 0, we have to deal with both of them at once. So finally, suppose C1 isn't 0 and C2 also isn't 0. Here's where we get things that are the sum of those two terms, not just one or the other. Then, as t approaches infinity, and what you want to do is to take each of those cases. What happens as t goes to infinity, what happens as t goes to negative infinity. Doesn't matter which order you think about them in, but you do have to think about both cases. As t goes to infinity, let's take a look at what each of these terms does individually. So as t goes to infinity, what's going on with this guy? Is it going to 0 or to infinity? Going to infinity, getting big as t gets big. So I'm going to say it goes to plus or minus infinity. That's going to depend on the value c, the c1. I'm not really so concerned about that now. I just want to know they go out as opposed to in. And c2 times that other term, 2e to the negative 7t, 3e to the negative 7t. What does that approach as t gets bigger and bigger? That approaches 0, the origin. So now let's think about what the sum does. So the trajectories, we'll take it that far. What will the x and the y do? Well, the x and the y are the sum of these two. So as time passes, the x and the y are approaching the sum of these things. In other words, they're going to approach infinity. They're going to be heading out. And this part of it is going to be pretty much negligible. This part is going to be insignificant, very unimportant. This part of it is going to rule. So we're going out to infinity, and this plus this will give us the x and the y. And since this is so close to 0, the x and the y are going to be very close to this. It might actually be better to look at it up here. If that part is practically 0, then the xy is almost the same as that, or at least getting very, very close to it. The mathematical term is asymptotic. So the trajectories are asymptotic to, well, they're going to be asymptotic to the line that corresponds to this term, which is the eigenline y equals 1 of x. Moving out to plus or minus infinity. On the other hand, as t goes to negative infinity, while I erase the board, perhaps you can kind of think through what happens this time. I'm not going to write as much this time. We'll just write down the conclusion. So as we look over here, as t goes to negative infinity, this term is going toward what? 0. And as t goes to negative infinity, this term is going toward infinity. So the sum is still infinity. We're still going out there. But this time, that one is practically not there. So the solutions are very close to the eigenline determined by the second term. So as t goes to infinity, to negative infinity, the trajectories are asymptotic to the other eigenline, y equals 3/2 x, moving out to, again, plus or minus infinity. And before I draw those in, I just want to make the point, get this in your notes. We use arrows to designate what's happening when t goes to infinity. In other words, I'm going to be drawing these solution curves. Every one of them has two ends. We want to put the arrow on the positive infinity end instead of the negative infinity end. And now I have to pull the board down and cover this, but I promise I'll give it back if you don't quite have it. All right, so what's going to happen is as t goes to positive infinity, my trajectories will be asymptotic to this. So it's going to be this sort of a picture. And that's where the arrow will go because that has to do with positive infinity. On the other hand, the negative infinity end, the trajectory approaches the other eigenline. And it probably wouldn't hurt to label my eigenlines. Y equals 1/4 x, y equals 3/2 x. So in each of these areas, that kind of thing happens. One end approaches this eigenline, that's the end that gets the arrow, and the other end approaches this eigenline, and I just drew an arrow, and that was bad. Got to erase that. And then we get some other ones in here, looking very similar, and over here, looking similar. So every other trajectory, and this whole thing is full of trajectories. You could draw infinitely many if you had the time. Every trajectory approaches this line asymptotically in its positive end, that line asymptotically on its negative end. Any questions? It's complicated. You kind of have to get used to the logic. Okay? Yes, Rudy.
I'm just making sure that you drew the second line when C1 equals 0 approaching the origin because x and y both approach 0.
Yes. Yeah, and x and y are the coordinates of the point. That's correct. Okay? All right, a few more things to say about this one. With this pattern, the equilibrium point, you know, all the interesting stuff is happening around the equilibrium point, but somehow it's the equilibrium point that we're going to name because of what's going on around it. So the equilibrium point, which is otherwise known as the origin, is called a saddle point. That's just the name that we give to this type of picture that surrounds the equilibrium point, where some things are moving in and other things are going out away from it. We call it a saddle point. With each of these pictures, each of these types of phase portraits that we draw, we're going to give the equilibrium point a noun and an adjective. So here the noun is a saddle point. The adjective is always going to be either stable or unstable. And the idea of stability is this. If you make a small change in initial conditions, do you get a small change in the results or do you get a huge change in the results? Let's look at this picture. If I'm sitting on the equilibrium point and I move just a little bit away in almost any direction, I'm going to land on a trajectory that sweeps me out to infinity, heads me out toward outer space. That's instability. If, on the other hand, actually there are just a couple of directions I could step that would bring me back close to it, and that would be if I land on the eigenline y equal 3/2 x. But almost any way that I step off the equilibrium point, I'm going to be heading out to infinity. So it is unstable. And then I'll just write what I said. Since most points close to it lie on trajectories, which move away from it. As t goes to infinity. One last thing to say about this example. This pattern is typical of systems having, I'll catch up there and then I'll let you help me with the logic here. What is it about this whole thing, and maybe we could just go back to the very beginning, what is it about this or this expression that pulls things in toward the origin? What is it that's causing that dynamic of things moving toward the origin? What thing right here at the very beginning?
E to the negative 17.
Yeah, it's the negative 17, because every time you let t go off to infinity, the negative 17, the e to the negative 17 pulls things down towards 0. What's the significance of the negative 7 originally? That was one of the eigenvalues. Now, what's the dynamic that pushes things out to infinity?
Positive.
That's the positive 3, the other eigenvalue. So the saddle point picture is typical of systems having one positive and one negative eigenvalue. Hopefully that makes sense. And that's the end of the first example. Do you have any questions? A lot of times you have to see 2 or 3 examples before you start to get a feel for the logic. Okay. Let's do a second. Second example. This time I'm not going to give you the original system, which I did here, but it's erased already, so never mind. It's in your notes. I'm going to go straight to the solution. That's where we can get everything we need. So C1, 1, negative 1, e to the negative t, plus C2, 1, 1, e to the negative 2t. And now hopefully you focus in immediately on the eigenvalues, because you found out that they really have an effect, a strong effect on the system. So the eigenvalues here are, where do you find them? Negative 1 and negative 2, there you go. So this is going to be a different kind of a picture, because it isn't one positive, one negative. It's both negative, so you would expect something different happening. We're going to go through the same kinds of cases, but I'm not going to write out nearly as much. We'll just kind of pinpoint the key things. So we're first going to let C2 be equal to 0, in which case we have x equals C1, 1, negative 1, e to the negative t. What you want to mentally do is think of this as a little x, little y. And so you say to yourself, little x equals C1 e to the negative t, little y equals the opposite of C1 e to the negative t. And if you like, you can actually write those things out. And somehow or other mentally, you want to come up with your eigenline, which is y equals negative x. This is actually easier than the last example because I didn't throw in any 4s or 2s or 3s, just 1s and negative 1s. So you can hardly miss with this one. Y equals the opposite of x. And let's think about what the trajectories are doing. Are the trajectories moving in toward the origin or heading out to infinity as time goes by? Moving in toward the origin because of that negative eigenvalue. So solutions or trajectories approach the origin. We'll start our picture in a bit. All right, if C1 equals 0, then of course x equals C2, 1, 1, e to the negative 2t. This eigenline is even easier than the last one. Y equals what? Y equals x. And this time, what are the trajectories doing? Are they moving in toward the origin again or heading out to infinity? moving in toward the origin. If you don't mind, I'm just going to use some ditto marks. Trajectories approach the origin. All right, let's go ahead and start our picture before we tackle the hardest thing, which is when neither one is equal to 0. Okay, so this time the eigenlines are very easy to draw. But again, I don't want to draw them going through the origin. I always want to put in my equilibrium point, then draw the trajectories on either side of that. So here I have y equals x, here I have y equals the opposite of x. And in all cases, the trajectories are approaching the origin. So with the first situation, they're in the second and fourth quadrants, approaching the origin along y equals negative x. And then in the second line, I have y equals x, but again, approaching the origin. So here's what it looks like so far. And I'm going to have to keep covering it up, but I'll also try to keep giving it back as we move on. So suppose neither coefficient is 0. That means that we have to deal with the sum of those two things. Again, we want to consider what happens as t goes to infinity. That'll be the end that gets the arrow. We want to consider what happens also as t goes to negative infinity. So as t goes to positive infinity, what's happening to both of those terms? They're both going towards 0 as opposed to toward infinity. So both terms approach the 0, 0, the origin, but which of those two approaches faster? The first one or the second one? The second one, because of that 2. So what's happening is that perhaps when you have a magnitude of, say, 1/10 here, you have a magnitude of 1 over 100 there. Or perhaps if you have a magnitude of 1 over 1,000 here, then here you're at a magnitude of 1 over 1,000,000. So this one's approaching 0 faster, which basically means this one rules. This one's stronger, more potent. This one becomes negligible or unimportant faster. Let's try to write that out. So both terms approach 0, 0, but the C211 e to the negative 2t approaches faster. So the trajectories are asymptotic to, you have to make sure you get the logic here. This one is unimportant comparatively, so that's the one that rules. So the trajectories will be very close to y equals negative x. And that's what happens as t goes to positive infinity. As t goes to negative infinity, and don't worry, pretty soon I'll give the picture back and we'll add to it. As t goes to negative infinity, now what happens to both terms? They're both going to 0 or infinity? To infinity. So both terms are going to go to infinity as t goes to negative infinity. So both terms approach infinity. But which one approaches faster? The first one or the second one? Again, the second one approaches faster because of that 2. But this time the conclusion is different. This one approaches faster. So for example, if that's around 10, this one's around 100. If that one's around 1,000, this one's around 1,000,000. So this rules, but here's the key difference. That one's not approaching 0. We cannot consider it negligible or unimportant. It still has a little bit of an effect, even though it's a smaller effect. So that one rules, but it's not a situation where something is asymptotic to something. Asymptotic means they're almost identical, which means the difference between them is close to 0. That's not the case. The difference here, which would be that, isn't close to 0. So here's what happens. As t goes to negative infinity, both terms approach infinity, but let's get this part down first. C211 e to the negative 2t approaches faster. We're all good so far with that. So, the trajectories here's what happens. The trajectories approach lines parallel to that second eigenline, which is going to be the y equals x. So the trajectories approach lines parallel to y equals x. So essentially, the y equals x rules, but the other one still is pushing a little bit, still having a bit of an effect, so it's not asymptotic but parallel. So let's see what it looks like when we put all that together. As t goes to positive infinity, the trajectories are going out, they're going in towards 0, asymptotic to y equal negative x. So that would be something like this. In towards 0, asymptotic to y equals negative x. And that was the positive infinity, so I am drawing an arrow on these guys. And by the way, don't draw them so that they look like they're coming in parallel or coming in and sweeping back out. Try to draw them so that it looks like they are really moving in toward that line. Now, at the other end, the negative infinity line, the trajectory approaches lines parallel to y equal x. So something like this, something like that. You can kind of see I'm trying to get them looking parallel-ish to y equal x. Same kind of thing here, same kind of thing here. I want to bend them around so it looks like they're going parallel to y equals positive x. So if I would draw more things in, again, there are infinitely many of these guys. They would look something like this. Whoops, I drew an arrow on the wrong end. That's bad. Arrow on this end, and same kind of thing over here. Any questions on that picture? So we had the saddle point picture. This one will have a different name. The equilibrium point is called, and I have to give it a noun and an adjective. So the noun is going to be a node, N-O-D-E. What do you think the adjective will be, stable or unstable?
Stable.
Stable, good for you. If you move off of the equilibrium point, you're brought right back down toward it. So you have stability, you're not headed out toward infinity. So the equilibrium point is called a stable node. Typical of systems having what? What's the dynamic here? What brings everything down toward the origin? 2 negative eigenvalues. Good for you. Any questions on that second example? Okay. I want to squeeze the third example. Oh no, it's already 11 o'clock. We'll wait for the third example. It's actually a short one comparatively, but we'll still wait for it till after break. During break, I'm going to pass out some blue pages and make sure that I tell you what that's all about after break. So if you head out for a restroom break or to get a drink, make sure you come on time, bring in on your own time, and we are then going to start on that third page on Tuesday. Now, that's not as bad as it sounds because I'm going to give you the fill-ins. So I will be posting today on Canvas something that says something like section 71.72, blue pages fill-ins. You just need to pull that up and go through it and write them in. So it's just the real super foundational stuff about vectors, not vector calculus, just vector algebra that I want you to do on your own time, and then we will pick it up on page 3. So that is why you get them today instead of Tuesday. All right, third example. The solution is x equals c1, 1, negative 1 e to t, plus c2, 1, 1 e to the 2t. Now, compare that example to the example that we just did. And what do you notice? Basically identical except for the eigenvalues have become positive instead of negative. So what are the eigenvalues here? Positive 1 and positive 2 rather than negative 1 and negative 2. So can you guess what the picture will look like? We're not going to take a lot of time to analyze. How do you think it will compare to this picture? Any guesses? Pardon?
They're out of going away from the origin.
Okay, exactly that. Everything's going to look exactly the same except for the arrows. You will get exactly the same eigenlines, you will get exactly the same trajectories. What you will not get are the same arrows. So the trajectories are the same. As in the previous example. Except that the arrows are reversed. The equilibrium point is what? How would you name it? Over here it was called a stable node. Over here it will be an unstable node. Same kind of picture. It's still a node, but this time unstable because everything gets swept out to infinity. An unstable node. Any questions on that example? Okay, example number 4. There's something that's completely different. X equals C1 times cosine 4t minus sine 4t over cosine 4t e to the negative t plus C2 cosine 4t plus sine 4t over sine 4t e to the negative t. Obviously a very different sort of solution, and it's a solution that comes out of what kind of eigenvalues? Imaginary, complex eigenvalues and eigenvectors. See if you can write down what the eigenvalues are that would have led to this solution. See if you can kind of think backwards from what we did last Tuesday and write down what eigenvalues would do the job. Who wants to be brave and tell me? The eigenvalues are? Yes, Rachel.
Negative 1 plus or minus 4i.
Negative 1 plus or minus 4i. Agree, disagree? You like that? Okay. You have fans. So the -1 comes from here. That's the alpha part. Alpha is -1. That's what ends up as a power on the E. And then the beta part is 4. That's the part that shows up as part of the sine and cosine expressions. So let's think through what's going to happen with this. So if I just think about, say, x in relation to t, x is a combination of sines and cosines. It's multiplied by, or within that we have some multiplication by e to the -t. So as far as x is concerned, that's horizontal motion. We've got oscillatory motion, but what's happening to the amplitudes of those oscillations? What's the effect of the e to the -t? What happens to the amplitudes?
Gets damped.
Yeah, exactly. They get damped. So instead of having x do this, x is doing this. It's oscillatory, but the amplitudes of the oscillations keep going down. At the same time, the y is oscillating with damped oscillations, damped amplitudes. If you kind of put those two motions together, what you get is a spiraling sort of motion. Both the x and the y are going back and forth, but the amplitudes are being damped. So you end up with essentially a spiral kind of a picture. Let me write all that out. Both x and y are damped oscillations. So the trajectories spiral toward the equilibrium point. Which is, now we have to classify it. So I'll let you catch up there. Reasonably enough, the equilibrium point here is going to be called a spiral point. Since the stuff around it is spiraling, does it look like it would be stable or unstable? Stable, because everything's moving in. So if you move a little off the equilibrium point, you continue to be drawn back in. So which is a stable spiral point. Now here I'm not going to do a careful sketch. I'm just going to do a rough sketch. So in other words, I'm not going to analyze the angles or which way it's going, clockwise or counterclockwise or anything like that. I'm just going to draw something that gives you a rough idea of what it looks like. You don't want to forget to put your equilibrium point in there. And then beyond that, you just have spirals coming in, something like that. And the spirals are all kind of intertwined. So another spiral would be coming in. They don't ever cross one another. Another spiral would be doing something like that. All of these spirals moving in toward the origin. And again, you'd have to do some further analysis to know exactly where those spirals are and whether they're going clockwise or counterclockwise, but that's just a rough idea. Now, what is it about all of this that draws the spirals in toward the origin and makes the system stable? In other words, what one little thing would I change? Yes?
The -1.
Yeah, the -1, exactly. It's that -1 that becomes the power on the E. That's what draws everything down towards 0. So if alpha is greater than 0, in this case the alpha was less than 0, but if alpha is greater than 0, the equilibrium point is, how would you categorize it? With everything else being the same, of course. What adjective, what noun? What's the only thing that would change? direction, and therefore, instead of calling it a stable spiral point, I would call it an unstable spiral point. Everything else the same. Okay, last example. X equals C1 cosine 4t minus sine 4t over cosine 4t plus C2 sine 4t plus cosine 4t over sine 4t. I'm hoping at this point you can kind of think through some of the dynamics in your mind. And in particular, can you tell me what the eigenvalues would be?
0 minus 4i.
Okay, plus or minus 4i. In other words, now we have taken alpha to be 0 instead of plus or minus 1. Let's think what happens here. Once again, both the x and the y are oscillatory. But this time we don't have damped oscillations or expanding oscillations. They stay the same size. So what do you think is going to happen? We'll go around and around, but we won't be drawn in or head further out. We're just going to keep on matching the same distance that we had from the origin. Now, we won't necessarily get circles, but we will get loops of some kind, usually ellipses. So this time, the trajectories are closed curves. The key there is closed. That's what's different from before. Moving around the equilibrium point. Which is, well, this time the noun is going to be a center, which kind of makes sense. And do you think this one's stable or unstable? Because this time nothing is either moving in or heading out. So which do you think would be appropriate? And again, the fundamental idea is if you change your initial conditions a little bit, if you just step a little bit off of the equilibrium point, are you going to stay pretty much in the same area, or are you going to be swept away to infinity? So I hope you can see that it is a stable thing because you stay basically in the rough area that you are, even though it's going around and around. So we call this a stable center. And again, I'm just going to do a very rough sketch. I'm not going to do anything careful here. There are ways to decide whether it's counterclockwise or clockwise and to come up with a better picture, but I'm just going to give you a rough sketch. Equilibrium point as always, and then you just have some things going around it. As I said, generally ellipses. And I'll draw it as if they're doing this, but you can't really tell unless you do some further analysis. Any questions on the phase portraits? Okay, we've got 10 minutes left, and that gives us enough time to just sort of chat about some of the applications and why we bother caring about systems of differential equations. So I'm going to begin this very last thing by saying there are, capital letter, underline, many applications of systems of DEs or differential equations. Here are a few. We obviously don't have time to go deeply into any of these or actually work anything out. So basically I'm just going to talk through some situations, some scenarios where a system of differential equations would be an appropriate model. So we're going to do 3 of them. The first one comes from the realm of sociology. And that's the idea of epidemics. So when you're talking about a system of differential equations, and here I'm going to think of this as having to do with 3 variables, an x, a y, and a z. My x is going to be the population of people that have not ever had this disease. My y is going to be the population of people who currently do have this disease, and the z is going to be the population of people who have had the disease but have recovered, so they are now immune. And the thing is that the x, y, z itself, those are levels. Those are how many people. It's just a raw number. Whereas a rate of change, a dx dt, a dy dt, a dz dt, tells you how that population is changing. And the thing is that dx dt does not only depend on x, it also depends on y and on z. Y does not only depend on y, but, excuse me, dy dt does not only depend on y, but on x and z and so forth. So for example, if I think about the y, the number of people who currently have the disease, and let's think about dy dt, that's the change in the number of people who currently have the disease. Do you see that that depends on x? Suppose that there are lots and lots and lots of people who have never had the disease. In that case, dy dt is likely to be a positive number. It's likely to go up because there are all these people out there waiting that haven't had their chance of getting the disease yet. Whereas if there is a very low number of people, if x itself is a small number, then dy dt is likely to be negative. The number of people that currently have it is likely to go down. Similarly, if z is a big number, if there are lots and lots of people that are immune to the disease, what do you think dy dt is likely to be? If you're following my logic so far, positive or negative? If there are lots of people that are done having the disease, they're immune, dy dt is likely to be negative because most likely the people that have the disease will be going down. Similarly, if if z is small, probably dy dt is going to be a positive number. But the point is they're interrelated. The derivatives depend on all 3 variables. So that's the first one. Second one comes from the realm of physics. And that is spring mass systems. And as you may already know, we're thinking about multiple connected springs. And if you imagine some kind of a system with multiple connected springs moving back and forth horizontally or however it is you set it up, I think it's this one. I don't need to even talk through so much. But you can see that the rate of change of the position of any of these springs is going to depend on the position of the other springs. So again, we have derivatives interrelated with all of the variables. And now we get to my favorite example. This one comes from the realm of biology. And that is predator-prey systems. Now, hopefully you have logged on to Canvas once in a while so far during the semester. If you haven't, that's a bad thing. What is my lovely picture? An owl and a mouse. Why? Well, really because even though I think, say, for example, a matrix is an exciting and wonderful thing, it doesn't look that exciting and wonderful. So I was trying to figure out some nice picture I could put on there, and most of the pictures just don't look that fun. So I picked an owl and a mouse because of this example. So we're referring here again to a system of differential equations, and I'm thinking about the owl population as compared to the mouse population in some ecosystem. So I hope it's reasonably clear that the relative size of the population, that would be the actual x and the actual y, will have an impact on the rate of change of those systems, the dx dt and the dy dt. For example, if x happens to be really big, if the owl population is high, what do you think that's going to do to dy dt, the change in the mouse population? It's probably going to be negative. It's probably going to go down if you've got lots and lots of owls. On the other hand, if you have lots and lots of mice, probably that means the mouse population will continue to grow, because the more mice you have, the more baby mice you're going to have. And so a high y value leads to an increasing or a positive dy dt. On the other hand, if the mouse population is big, if the actual y value is big, what do you think about dx dt? Positive. Probably the owl population can go up because it's got lots of things to feed upon and so forth. So again, you can talk through the various scenarios and interrelationships, but I hope the point is clear that systems of DEs, interrelationships among not only the actual values but the derivatives of those things, the rates of change, very common, very applicable. Any questions? Okay, that concludes the matrix unit. I've got 3 minutes left. I won't talk too much more, but I just want to make sure, for the sake of those folks that were still coming in after break, that you know about the blue pages. First of all, does everybody have blue pages? Raise your hand, complain if you do not. Okay, that's good. This is the beginning of the matrix, excuse me, not the matrix, the vector calculus unit. We're going to have lots of blue pages in the first couple of weeks. This is the first packet, not the only packet, but I'm asking you to do the first 2 1/3 pages on your own, section 7.1 and 7.2, but the fill-ins will be posted on Canvas. You don't have to go searching through your memory or through books trying to figure it out. Any questions? All right, have a good weekend. Stay warm and dry. I appreciate y'all being here today, and I'll see you on Tuesday.